Okay, so momentum and conservation of momentum and impulse. We finished, and now we're moving on to work, power, and energy. Okay, so this would be a whole new unit, and it's gonna have a number of different pieces in it. Okay, today we're gonna look at just work. Now, I am 100% sure that you all have heard of work before. Some of you have maybe even done work. It's always good to hope, at least. But the way the world talks about work and the way physicists describe work are not exactly the same. You can see the parallels once you know what we say work is in physics. But in the rest of the world, they're a little bit looser, a little bit slacker with how we define work. Okay, so we, physicists, define work as happening when a force is applied to an object causing the object to move in the direction of the force. When a force is applied to an object, causing the object to move in the direction of the force, work is done on the object. All right, so this should make sense if you think about, you have a box and you're going to push this box down the hallway. So you push with the force parallel to the hallway and you move the box some distance down the hallway in the same direction that you're pushing. And when that happens, work is done. If you were standing in a classroom and you were holding a textbook in your hand, so you're definitely applying a force to the textbook because gravity be pulling it down. So you must be putting a force on the textbook. Okay? And now you begin to walk around the classroom. So your V is this way, or your delta D is this way. Are you doing work on this book? So you're putting a force on the book, and the book's moving, but there's no work being done here because the object is not moving in the direction of the force. Okay, so the force and the direction that the object's moving has to be in the same direction. So in this first picture, work is being done, but in this second picture, it isn't. And that's where, like, my muscles will get sore, and at the end of the day, if I'm carrying this book around the whole day, it will feel like I'm doing work. I will feel tired, but physics-wise, no work is being done. Just the same as if I stand there and just hold the book in my hand all day. No work is being done because then the object isn't moving at all. Okay? Or maybe because I'm feeling particularly strong, I decide to push on that big lab bench in my classroom. I can stand there and push all day and all night. I'm definitely applying a force, but I'm not doing any work because that lab bench is firmly secured to the floor and it's not going anywhere. Okay, another little interesting note is, so I'm going back to my box. Imagine if I was pulling with a force upward at an angle. And my box, though, is moving this way. So this is my delta D. The object has to move in the direction of the force. Well, the object isn't going to be moving upward at an angle. The component of this force that's making the object move is my Fx. And if I draw in the rest of my triangle, we know that my Fx is the adjacent side, so cos theta will equal Fx over F. So Fx will equal F cos theta. So it's the F cos theta part of the force that's making this object move. And that becomes important when we think of, so what's the equation for work done? Work done is directly related to, directly proportional to the amount of force you apply and the distance that the object moves. But it is also dependent on the angle between them. And so work done is equal to F delta D cos theta. Okay? F delta D cos theta is our equation, where F is the force applied, delta D is the displacement of the object, and theta is the angle between them. So F, force applied, and of course that's in newtons, delta D, displacement of the object, and of course displacement is meters, and theta, the angle between the F and delta D. Okay? Now, if we go back to my examples then, here the angle is 90 degrees. And if you pick up your calculator and type in the cos of 90, you'll find out it's 0. And so then no matter how big the F is, no matter what the delta D is, if the cos of 90 is 0, this whole thing goes to 0 and you're not doing any work. Whereas here, the angle between F and delta D is 0 degrees, and the cos of 0 is 1. And so you're doing maximum work when you're pushing in the same direction as the delta D. In the third picture here, it's only a component of the force that's doing work. And so you can put either the whole value in here, right, the F, and then that's where the cos comes from. The cos theta is as if the equation is taking the component for us. So in work, we never have to do what I did here. I just wanted to show you where this cosine comes from. Okay, so if the force is acting at an angle, then this cosine takes the component of the force that is causing the work to happen. All right, so W, I did the F, I did the delta D, I did the theta. So then W is the work done. And if you look at the units, it's going to be Newton meters. So it's measured in a Newton meter. And that is what we call a joule. So the other day I told you energy was measured in joules, so is work, okay? And it's a capital J. You will get maximum work if the angle between F and delta D is 0 degrees. You'll get maximum work. You'll get minimum work, or no work, if the angle between F and delta D is 180 degrees. No, I lied. It's 90 degrees. Sorry, I'm jumping ahead. Right? If the angle is 90 degrees, this is no work done, which is minimum. If the angle between them is 180 degrees, you will get negative work. And what that means is you don't have to do work on the object to make it move there. The object itself wants to go there. Whereas here, this will be positive work. So whenever you get a positive value for work, it means you actually physically have to do the work. So lifting a book. So if you're actually, here's a book, you're applying a force to it to lift it up, and the book is going up. You're doing positive work on that object. But then if you were to, that book is now, you're holding it up high, and now you're going to lower it. You still have to put a force upward on the book when you lower it, because if not, it's just going to fall, right? When you lower a book, or if I lower this pen, it's not that I'm not putting any upward force on it. I am. It's just, it's equal to balancing out gravity, so this doesn't free fall. So going down is the delta D. So now the angle is 180, and I get out negative work. And what that means is that really the object is losing energy, and it's really gravity that's doing the positive work. So when I do positive work, and I'll go back to this in the next video, but when I do positive work, it means I'm increasing the energy of the object. And negative work means I'm